I'm going to run this exact same program 3 times in a row, and I'm not going to change a single line of code between runs. Watch the number at the bottom. 3 runs, 3 different answers. Same code every time. This is a race condition, and by the end of this video, you'll understand exactly why this happens and how to fix it. Before we get to the bug, let's define a thread. A thread is a sequence of instructions your program executes, and a program can run multiple threads at the same time, genuinely simultaneously if you have multiple CPU cores. Here's the important part. Threads within the same program share memory. If thread A and thread B both need to update the same variable, they're both reaching into the exact same box in memory. Nothing stops them from doing that at the exact same moment. Here's the part that breaks people's intuition. In your code, counter plus plus looks like one single step. But at the CPU level, and if you've touched assembly language, you already know this, it's actually 3 separate operations. First, read the current value of counter into a register. Second, add 1 to that register. Third, write the register's new value back to counter. 3 separate steps. And critically, the operating system can switch from one thread to another at any point between those steps, including right in the middle. Let's walk through exactly how an update gets lost. Thread A reads counter, it's 0. Before thread A can write its new value back, the operating system switches to thread B. Thread B reads counter, it's still 0 because thread A hasn't written anything yet. Thread B adds 1 and writes counter as 1. Now, thread A resumes right where it left off. It already read 0 earlier, so it adds 1 to that old value and writes counter as 1 again, completely overriding thread B's update. 2 threads each tried to increment the counter once. The counter should be 2. It's 1. One entire increment just vanished, and neither thread ever knew it happened. Here's the actual code. 2 threads, each incrementing a shared counter 1 million times. If nothing went wrong, the final count should be exactly 2 million every time. Every run gives a different, wrong answer. That's the signature of a race condition. It's not consistently broken. It's unpredictably broken, which is exactly what makes these bugs so dangerous. They can pass testing 100 times and then fail in production once. The fix is a mutex, short for mutual exclusion. Think of it as a lock around those 3 steps. Only one thread is allowed to hold the lock at a time. If thread A is inside, doing its read-add-write sequence, thread B has to wait until thread A is completely finished and releases the lock. This guarantees the 3 steps happen as one uninterrupted unit. Exactly what we needed, since the bug only happened because those steps could get split apart. Same idea, same 2 threads, same 1 million increments each, but now wrapped in a mutex lock. Every single time, exactly correct. That's what a fixed race condition looks like, not faster, not fancier, just reliably, boringly correct. So that's a race condition. 2 threads, 1 shared piece of memory, and an operation that looks atomic in your code, but isn't atomic to the CPU. The fix is always some form of controlled access, a mutex being the simplest version. This isn't just an academic bug. Bank balances, inventory counts, anything with shared state across multiple threads or processes can hit this exact problem in production. Understanding it here means you'll recognize it instantly when it shows up somewhere far more expensive to debug. Subscribe, and I'll see you in the next one.